Hello everyone. So let us continue our discussion on molecular orbital theory. So previously I talked in general about how the atomic orbitals are combined to form molecular orbitals in a hypothetical AB molecule. So we tried to define how we are able to find the wave function for a molecular orbital. So today we are going to look into a real example. So we'll take the H2 molecule. So we can consider H2 to be, we know that it's a combination of two hydrogen molecule or hydrogen atoms. To differentiate them, I have written it as HA and HB, leading to the formation of H2. So how we are going to see how the molecular orbital wave functions we are trying to understand. So each of these hydrogen atom has their corresponding wave functions represented as chi HA for atom A and chi HB for atom HB. Okay, so as I told you in the previous discussion, in order to form the molecular orbital wave function, we linearly combine them. Now here I would like to introduce another important salient feature about the molecular orbital theory, which I discussed previously, is that the number of molecular orbital that is formed depends upon the number of atomic orbitals that are combining. So here there are two atomic orbitals, okay, that are combining. That is, we are doing the linear combination of atomic orbitals. So obviously it should lead to molecular orbitals. The number should be 2. So that's why I have written one of the molecular orbital as chi H2, another as chi star H2. Now what are these? I'll just now explain to you. So when we do the linear combination, as you remember, there was a constant n and C1 and C2. So here C1 and C2 would be the same because both are hydrogen atoms, so they can be taken out as common. So in order to understand the physical significance, we are ignoring the constant n and C, which has been taken out as common. So when we talk about the linear combination of the two wave functions, if you remember when I talked about the shapes of the various atomic orbital, I talked about these signs such as plus and minus, which are actually the phase signs that are coming as a result of the solution to the Schrodinger wave equations. It has nothing to do with positive or negative charges, but rather they are mathematical signs that are coming on these wave functions. So when you have two 1s orbitals combining, in the case of hydrogen, they having same phase sign, we say that the combining orbitals are in phase. Okay, so that means we literally linearly combine them. Both of them are positive wave functions, so it is a addition kind of phenomenon that you observe here while linearly combining them. Now in another case can be one of the 1s orbital have a phase sign that is opposite to the combining atom. So in such a case we say that they are out of phase. Okay, so when they are out of phase, when both the phase signs are different, when we linearly combine, one of the atom is going to have a negative wave function because the phase sign is negative. So it would be like a subtraction of the two wave functions of the atom. Now you can go ahead and do that. Chi square H2 or chi star H2 square, when you do, one of them would lead to plus 2 chi HA chi HB, and this one would lead to minus 2 chi HA and minus HB. So here it led to, so if you remember, 2AB term was the overlap integral. So when we the overlap integral actually gives you the extent of bonding. So when it is a positive overlap, it leads to bonding. When it is a negative overlap, it leads to anti-bonding. That means there is no bonding that is happening in that case. So the first case where the both the wave functions are in phase, it leads to a constructive interference of the wave functions, leading to what you would call it as the bonding orbital in a molecular in the bonding molecular orbital as what is formed here. When it is a destructive wave interference between the wave functions happening, it leads to a negative overlap, or it leads to an anti-bonding molecular orbit. So let us try to understand them figuratively how it is done. So basically in the case of hydrogen atom, it is basically the overlap of two 1s orbitals. So here you can see we have an in-phase overlap because both of them are positive sign. So when they overlap, this is a valence bond theory. Its overlapping thing was a phenomenon that we define in the valence bond theory. So I told you when the atomic orbitals overlap or bonding happens, this overlap leads to a common kind of a new set of orbitals, which is now called as the molecular orbitals. So you can see now these are not kind of localized on these nuclei, but like it is over the whole molecule. So this whole molecule contains two nuclei of hydrogen atoms. So this bonding electrons belong to both the nuclei in common. So that is the difference between a valence bond theory and a molecular orbital theory. So it's a positive overlap leading to a bonding overlap. So in the same case, same way, when there is a head-on overlap happening, it leads to a sigma bond formation that has been borrowed on in the molecular orbital. So when the orbitals are kind of overlapping in a kind of head-on fashion, it leads to sigma molecular orbital. So that particular part has been borrowed from the valence bond theory. Now when the two wave functions are opposite or out of phase, it leads to an anti-bonding. So there is no bonding happening, but rather a node is generated. Now node is a place where there is no probability of finding an electron. So this is the node here. So you can see these electron clouds are directed away from each other. So this is how you represent an anti-bonding molecular orbital. So here you do not have any literal bonding, but rather a nodal plane is generated. So this is referred to as the anti-bonding molecular orbital. So here an important thing you have to note is that when the two atomic orbitals wave functions you are combining, it leads to two molecular orbital. One is bonding and another is anti-bonding. So this is always the case when there is combination of two atoms happening. So if suppose there is a combination of s and p orbital, okay, here we have a combination of this p orbital and this s orbital. So when the lobes are in phase, it leads to a positive overlap leading to a sigma bond and bonding or molecular orbital. And when they are out of phase, it leads to no bonding and a node is generated here. So that is called as sigma star because it is a anti-bonding. So anti-bonding orbitals are usually designated as sigma star. Okay, so this is anti-bonding molecular orbital and this is bonding molecular orbital. Let's look at when there is two atomic orbitals that are p. Both are p orbitals. So when the two p orbitals are in phase, it leads to a bonding molecular orbital. So since it's a head-on overlap, it's a sigma kind of molecular orbital. So it is a sigma p orbital leading to a bonding molecular orbital here. Now when they are out of phase, it leads to no bonding and a node is generated in the process and it is sigma star. So always a corresponding thing is what is formed here. So sigma, then the sigma only here again. So it is sigma star because it is anti-bonding. There is no bonding happening here. Now, the p orbital, rather than having a head-on, it can also have sideways or lateral overlap. This we saw when we tried to understand ethene and ethine molecule in the valence bond theory. So when both the signs are in phase, sideways overlaps are in phase, it leads to a pi molecular orbital and bonding nature. Okay, so when they are positive, it leads to a uniform positive on the upper side as well as on the bottom side of the internuclear axis. However, when they are not in phase, that means they are out of phase, there is no bonding happening. They are like directed away from each other and a node is created in the process. So this is a pi star. A star is missing here. There should be star here. So this is a pi star and it's anti-bonding molecular orbital. So it is a pi overlap here because it's a lateral overlap that is happening. That's why it's called as a pi overlap here, and pi star in this case because it's a anti-bonding molecular orbital. Now here an important thing that you have to note here is there are certain requirements for the combining atomic orbitals. One important fact is that the atomic orbitals must be having roughly the same energy. Okay, you cannot have combination of atomic orbitals different in energy. Second important point is there should be a maximum overlap between the two atomic orbitals. If there is no proper overlap between the atomic orbital, it will not be considered under the linear combination of atomic orbitals. Another important thing that you have to note here while using the linear combination of atomic orbital is that they should have similar symmetry about the internuclear axis. Okay, so so when you can see here internuclear axis, there is no change in the sign of the so that's why they are able to be combined here. Here the internuclear axis, when you see there is a uniform change, when you move up this becomes negative and this also becomes negative. Like I mean to say, both the sides atoms that are combining are having same phase signs. Okay, so when such situation happen, it leads to a kind of symmetry in the combining atomic orbitals, and that's why that is an important factor that is needed while you are using the linear combination of atomic orbitals. And here, like the electronic configuration, you have in the increasing order, you have certain orbitals which are termed as the molecular orbitals. Okay, so molecular orbitals look similar to the electronic configuration that you write for the atomic orbital. So the lowest energy is the 1s, then 2s, then 2p. So this is only you are considering right now. You are not going into the higher forms. So it's sigma because the s orbitals, when they overlap, it's more of a sigma kind. So it is sigma 1s. So obviously it will also have a sigma star, then sigma 2s, sigma star 2x. Then p orbitals, one of the p orbitals would be involved in sigma bonding, and another orbital would be involved in pi kind of, other two p orbitals would be involved in pi bond formation, and they are usually doubly degenerate. That means both these molecular orbitals related to p orbitals are degenerate in nature. Okay, and we have two different types of these electronic configurations because of certain spectroscopic studies, it is found that B2, C2 and N2 have this electronic configuration. However, O2 and heavier elements have this particular electronic configuration. Please kindly go through these electronic configuration and try to understand how it is written here. And in the next video, we will quickly describe a little bit more about this electronic configuration. Thank you very much.